Welcome everybody to the next in our seminar series. Today, very lucky to get Jack with us. Jack's currently a postdoc at OSU. He's been at OSU for the last 3 years. And prior to that, he did his PhD in Manchester with Sarah Bridle. He's been instrumental in leading the large-scale structure analyses of the dark energy survey. And he's going to tell us more about that today. Okay, thanks, Jack.
Excellent. Thanks very much. Okay, so so as Will said, I'm going to tell you about some work from the Dark Energy Survey, some of the cosmology results that we released this summer. So this is mostly working on Dark Energy Survey data, looking at galaxy clustering and galaxy lensing, and what that can tell us about cosmology. So I'm going to structure the talk as first as an introduction of what it is scientifically that we want to probe, what we want to understand from Dark Energy Survey data. And then I'm going to split the rest of the talk into two, first focusing on the lensing and clustering analysis. This is our DES combined probes analysis with a primary aim of constraining dark energy equation of state parameter. And then I'm going to spend the last 10 minutes or so talking about our BAO analysis. So this is our geometric probe, which is designed to measure or add a data point to the history of the universe's expansion at late times. Let's start with the model that we're trying to test. So the basic aim of, I think, all of these analyses is as a robustness test for the lambda CDM cosmological model. So this is our standard model with around 30% matter contributions and about 70% contributions from this unknown dark energy causing the expansion of the universe. We assume that this dark energy component is a cosmological constant with equation of state -1. This is your negative pressure cosmological constant contribution, and we assume that the universe is flat. This is the basic concordance cosmology model that has come over the last, sort of emerged over the last 30 years or so, and with parameters primarily constrained by the cosmic microwave background. And so this implies a history of the universe, I'm sure you've all seen before, where we start off with after the Big Bang, a period of inflation. There is a surface of last scattering from which we can measure the cosmic microwave background, and then we can evolve that model in time into the late time universe, where we are dominated by a dark energy component, which is causing the universe to expand with an accelerated rate. And so the basic idea, at least for the purposes of this talk and the sort of structure formation perspective of cosmology, is that we're going to compare results from the early universe, from the cosmic microwave background, mostly looking at results from the Planck collaboration. And we're taking this within the lambda CDM model and evolving the observations of the CMB down to late times, where we can measure sort of the local or late time cosmological observables. The one that I'm focusing on today is large-scale structure probes of lensing and clustering. And this is all designed to measure the late-time galaxy distribution and statistics of the late-time matter distribution. And this is sensitive to the growth of structure and the geometry of the universe, which can both have their own CMB predictions within the lambda CDM model. And similarly, you can also measure this with supernova or other sort of distance ladder measurements that can probe your expansion rate at late times and compare that to the early universe. And so the question we want to ask is, does this model work with observational data? There are lots of questions about it theoretically, but if we're just thinking of this from an observational point of view, does this model work? And the answer is sort of. There's a known tension within this model where late time and early time measurements of the Hubble constant, so the total expansion rate, or the redshift zero expansion rate of the universe, appears to be different between the local measurements and the CMB. And this is kind of now a 4 or 5 sigma discrepancy between the two measurements of early time and late time. And then some hints that the large-scale structure measurements at late times also have a different structure fluctuations, so a different sort of amplitude of the matter fluctuations at late time compared to the CMB. This is less statistically significant, but it is still an intriguing question. So the picture that we had 1 year ago before before the latest DES results showed. So I'll get into some more of the details on what these contours exactly mean, but the general idea is that we're looking at a plot of matter fluctuations. So this is the amplitude of your matter power spectrum, the amplitude of so how clumpy your matter distribution is versus the total matter density, omega matter. And the large-scale structure probes, which are these three contours below, which are the late-time probes, are generally finding slightly lower sigma-8 values, slightly less clustering than you would expect compared to the CMB at early times. Each of these individually is only a couple of sigma, so you wouldn't worry about those by themselves, but because all of the experiments are finding low values, and it's very difficult to combine them in a statistically robust way, this has made people very interested in the idea of, can we shrink these contours down and really test whether this discrepancy is real? And that's what we want to do with the dark energy survey. So for people who are unfamiliar with DES, dark energy survey is a photometric redshift survey based in Chile. It is measuring a 5,000 square degree patch of the southern sky over 6 years. So those observations are now done. We've only analysed the first 3 years of that data. So the analysis that came out in the summer was our year 3 analysis that I'll be talking about, and then we've got a year 6 analysis to come with the full data set. But year 3 covers the full area, but only at half depth. So we've measured 5,000 square degrees, but only to half the depth that we intend to measure with DES. And the survey overall is using galaxy clustering, galaxy lensing, the counts of galaxy clusters, and supernovae. It has all 4 of these cosmological probes to measure dark energy parameters. And the 2 that I'm focusing on today are the galaxy clustering and galaxy lensing parts that I've worked on. So the observables that we're looking at are, there are 3 different observables that are important to this talk. The first is cosmic shear. So the little cartoon here shows these little white ellipses represent background galaxies, and the red circle represents some foreground galaxy or foreground massive structure. And you can see that because of gravitational lensing, the background galaxies are sheared, so their shapes are modified tangential to the line that connects them to the foreground mass. So if we measure the autocorrelation of the shapes of the background galaxies, so how aligned are 2 galaxies separated by some distance, we call that cosmic shear. This is our pure lensing cosmological measurement that is sensitive to all the matter between those galaxies and us. The second measurement that we have is the cross-correlation between some foreground sample and those background lenses. So we sometimes call this galaxy lensing, sometimes called tangential shear, but the purpose is you're trying to say, if you have a galaxy separated by some distance from the foreground, how likely is it to be sheared tangential to the line that separates them? And the third is the galaxy clustering signal, where I spend most of my time, and this is asking how likely are we to find 2 galaxies close to each other, separated by a given distance. And by combining all 3 of these probes, you can break internal degeneracies and get cosmological constraints on structure growth, on the total matter density, and a number of other things, all from one analysis. So we refer to this usually as the 3 times 2 point combination, because it's using 3 different 2-point correlation functions to constrain your cosmology. The galaxy clustering signal also has other information that we can use from baryon acoustic oscillations that I'll hopefully mention at the end of this talk. And so just a quick overview of why 3 times 2 works. So a galaxy clustering signal, an angular galaxy clustering, so this is just using imaging data. So we basically have the clustering tangential to the line of sight, and we can do that in slices of redshifts, but we don't have the redshift resolution to measure along the redshift direction. And so when you do that, and you just have that angular clustering signal, what you're measuring is perfect degeneracy between omega matter, by sigma 8, which is the amplitude of matter fluctuations. This is the quantity that is cosmologically interesting, and this galaxy bias, which is telling you how likely are galaxies to sit in overdensities of a particular size. And so this is also astrophysically interesting, but for our purposes, we consider this to be kind of a systematic, that we are unable to measure the cosmological parameter from clustering alone because of this galaxy bias. Luckily, galaxy-galaxy lensing, which is this cross-correlation between your background lenses and your foreground, has the same issue, but with a different degeneracy direction. And so when we combine those two, we can measure what we call the 2x2, or informally within DES we call the 2x2 analysis, that combines these two-point correlation functions to simultaneously measure bias and sigma ray. The cosmic shear, which is the lensing-only analysis, is purely a measure of sigma 8, although not always as precise. That depends on the specifics of the survey. And so we can combine this as our third two-point correlation function as a robustness test on your 2x2 results. And is also very cosmologically interesting by itself. So for DES, how do we do this? So for the DES analysis, we have a sample of around 100 million background source galaxies. So these are the galaxies that we have measured ellipticities for. They tend to be the fainter galaxies in our sample, and we measure sort of as many shapes as we think we can. We believe this is the largest shape catalogue that is sort of weak lensing ready that exists. If anyone knows of others, feel free to correct me. And then there are two foreground, what we call lens samples, that are used for the galaxy clustering measurements and as the cross-correlation in these tangential shear galaxy lensing cross-correlation measurements. And the idea of our analysis is that we do this in parallel between a selection of red foreground galaxies, the idea here being that we have a low number density, but really good photometric redshifts. So by calibrating with the spectroscopic sample and trying to select only galaxies that sit right on the red sequence, we think we can understand the photometric redshifts of these galaxies, but there aren't that many of them. And then there's an analogous approach that uses a magnitude limited sample. So this is just saying select any galaxy above a given flux. And here you have more uncertain photometric redshifts, so you have to deal with that systematic, which can be a pain, but you get better statistics. So we have around 3 times as many galaxies. And in both cases, we are the idea is that you are selecting a good group of foreground galaxies that you can use to anchor your redshift information in your analysis. We split each of these samples up into tomographic redshift bins. So for the red magic sample, we split it into 5 bins, and then the photometric redshifts are determined by this comparison to the red sequence in spectra. Our magnitude limited sample, it's called MagLim, is we measure our redshifts through machine learning techniques and split this into 6 redshift bins, so we can push this up to higher redshifts, which is interesting, although we only use the first 4 in our fiducial analysis, to those ones we trust our redshifts the best. And then in our source sample, so this is the galaxies we have ellipticity measurements for, we split into 4 tomographic bins, but as you see, these are much wider distributions, and so we have, because they're fainter galaxies, we are less certain of their distances. And this is all calibrated with image simulations in a number of papers with a number of innovations that I won't have time to talk about today, but they're described in these papers, and there's a lot of interesting developments that DES has implemented to get a reliable measurement of these redshift distributions. Okay, so the basic premise here is that we have 3 samples of galaxies. Any 2 of them are used in one 3x2 point analysis, and we split each one into tomographic bins. So this is a scary flowchart. You don't need to worry about all the details of this. I'm not going to go through this individually, but the purpose here is to demonstrate that this is quite a complex analysis. So the boxes on the left generally show things that we need to do with the pixel level data itself, so the actual images of our galaxies, and how do we get from images to galaxy catalogues with shapes and positions and redshifts all reliably measured. And then the right-hand side is where we measure our 2-point correlation functions, and then finally, and all our theory measurements, so our model and our covariance matrix for the 2-point measurements, and finally do our cosmological inference. Each of these boxes, I think pretty much all of these boxes turned into a paper that has been released over the last year. So this kind of just demonstrates how much work needed to go in to finally make these final contours that I'm going to talk about, and how many people were required to do. And then so I'll quickly flash up. These is the photos of all the people who worked on the 3x2 analysis who were willing to give their photos. You might notice a face or two from Waterloo. It took a very large group of majority early career scientists in order to get that analysis to produce cosmology results. Before I show you those results, I'll have a quick mention of the model so that everyone is on the same page. So what we're doing here is we're trying to predict these 3 correlation functions that we can measure with our data. And in order to do this, you need to input the 6 standard lambda-CDM cosmological parameters. So these are things like omega matter, your total matter density, the amplitude of your power spectrum, and so on. And then a dark energy equation of state, which we allow to vary when we wish to constrain it. And then a large number of systematics parameters that are all calibrated from the data. So we have systematics from photometric redshifts that quantify our understanding of how much we trust our calibration. The intrinsic alignment of galaxies, so that's how likely it is for 2 galaxies to be aligned with each other due to non-lensing reasons. And also the uncertainty on our shape measurements itself. We also added this new systematic, well, new for DES, that hasn't previously been required to measure in the past generations of weak lensing surveys because we weren't sensitive enough to it, but this is lens magnification. So this is how likely it is for a background galaxy to enter or leave your sample because its total brightness and position is being modified by your foregrounds. So not just looking at the change in galaxy shear or ellipticity, but the actual likelihood of the galaxy being in your sample in the first place. And we have a paper in prep describing this lens magnification systematic. This all results in a large multi-dimensional parameter space in which we can constrain our data. We put some tight priors on some of these systematic parameters, and then ultimately the inference that we're doing is trying to constrain just a few of these lambda CDM or WCDM cosmology constraints. And our fiducial analysis, we have 4 lens redshift bins from the magnitude limited sample, but I'll talk about the others a little later. So, and also I'm just going to flash these up. Again, don't need to worry about all the many data points. This is our actual correlation function measurements that we have from the DES data, split into the 3 sections. So this is the cosmic shear, autocorrelation of your shapes, your galaxy-gas energy cross-correlation. So this is a 4x4 grid from your 4 lens redshift bins and your 4 source background shaped galaxy bins. So that gives you a total of 16 correlation function measurements. And then we measure the autocorrelation of the positions, which is our galaxy clustering signal for those 4 magnitude limited bins. So what this results in is a very long data vector that we then plug into that model and see what the inference it gives us. This analysis was all done blind, and so we didn't look at any of these points or make any inferences from these until we were satisfied that the model and all the systematics had been fully dealt with. So we plug this into our analysis. What do we find cosmologically? So these are so I'm now going to go through some of the headline results from the DES analysis and what this tells us about the lambda-CDM model. So the first result is to say, is the DES data internally consistent? So the blue contour here is cosmic shear, so this is lensing only information, and then the orange contour is this 2x2 combination. So this is the combination of galaxy clustering and tangential shear. So this is this is basically a way for us to split the 3x2 cosmology analysis into two independent or semi-independent ways to constrain structure formation. And again, this is looking at lambda CDM model with the total matter density against the total clustering amplitude. The clustering amplitude here is S8 rather than sigma 8 because we are modifying our parameter space to best align with the degeneracy direction that weak lensing experiments typically find. The physics is ultimately the same. And what we see is that the clustering and lensing combination and the lensing only results are perfectly consistent, as you might expect. And that is backed up by our independent tension metrics, so our more statistically rigorous tension metrics that take into account the full multi-dimensional parameter space rather than just this 2D projection. And so because they're consistent, we can combine them into this 3x2 result. So this is one of the headline cosmology results from DES so far. And it's our lambda CDM constraint on the clustering amplitude and matter density from this 3x2 combination. You'll see that this is slightly higher than the overlapping region due to degeneracies with the other 30 dimensions. Okay, so the first question you want to ask when you've got your 3x2 cosmology result is it consistent with the CMB? And this is one of the fundamental questions that we want to answer. Does the CMB adequately predict late time clustering measurements? And the answer from the DES result appears to be yes. So this is, the green contour here is the prediction from Planck, and then the grey is our headline lambda CDM result, and there is only sort of a sigma between the two. So this is less tension than some of the other lensing experiments have found, which have typically been a couple of sigma, if you consider that, if you consider tension to be the appropriate word there. And so it does appear that DES was, while we were capable of breaking lambda CDM with a few sigma tension with the CMB, that's not what we found. And so we're currently saying consistency with the CMB. And and so a reminder of what that looked like before the DES year 3 result. So this is pre-DES year 3 on the left and our headline result on the right. And you can see we're basically constrained right in this little overlapping region here. So exactly the kind of region that you either want or don't want, depending on whether you want to break this cosmological model. The good thing about the consistency is that we can then combine those data sets. So the red contour is the DES headline result plus the cosmic microwave background, and then you've got your total lambda CDM. This is what we think the structure parameters look like when we combine all the latest data available to us from a DES perspective. The nice thing about this is that you can then extend your standard model to whatever extension is interesting to you, and you can use you can always use the combination of DES plus Planck to put upper limits on your models. So we can do this with dark energy, we can do this modified gravity, whatever it is that you're interested in that affects late time structure. The one that we've released so far is looking at just the dark energy equation of state. That's what this figure shows here. So this is looking at the dark energy equation of state versus omega matter in a slightly different parameter space, where we basically added one extra free parameter. And you can see that DES alone gives you, DES alone gives you a moderate W constraint by itself. The CMB gives you a moderate W constraint by itself, but when we add those together and you can also add other low redshift spectroscopic information, you get these really tight little contours that are really hard to see on these plots because they're such tight constraints. And what this ultimately gives us is a 3% measurement of the dark energy equation of state, which is remarkably tight, but is consistent with W equals -1. So the numbers shown here are this is the mean of our posterior distribution, and this is our best fit value. And so just by some statistical fluke, our mean, our best fit value appears to be sitting basically bang on dark energy equation of state equals -1, which is an interesting result. Okay, so those are our sort of headline results. That's what we think DES was able to tell us. So if you're a cosmologist who's interested in the headline takeaway result from DES, that's what we can say. What I'd like to do now is to go in a little bit more detail about under the hood, what do we find that's unusual about the DES results, and where do we think that the focus should be over the next few years, because we have cross correlations with DESI, we have LSST, the Rubin Observatory, we have Euclid, we have all these experiments that are going to be measuring similar 3x2 analyses to this one, and we need to know where to focus our efforts to make sure that those are not systematics dominated. So I mentioned earlier that we had these two examples, two foreground lens samples. So this is our magnitude limited sample, which was the fiducial, and our red selection we call red magic. We do these in parallel, and we find that if you just do the full 3x2 cosmology analysis in parallel between the two analyses, you get almost exactly the same cosmology results. So initially you think, great, done, we've shown consistency, there is some obviously some covariance between the two measurements, but it appears that we're giving the same broad cosmology constraints. However, when you split the red magic analysis into the two constituent parts, the cosmic shear and the galaxy clustering plus tangential shear, 2x2, that internal tension appears to lessen somewhat. So by the metrics that DES used within the 30-parameter space, 30-dimensional parameter space, these were formally consistent, but I think you can clearly see that the 2x2 analysis is predicting an unusually low clustering amplitude, so it is at the very least worth doing a sort of post-unblinding investigation of why that happened, to try and understand what it is about these red galaxies that was giving clustering information unusually low. And so the important thing to remember here is that because we have three correlation functions, any two of those correlation functions can predict the third. So if you know your lensing information, you know your clustering information, you can perfectly predict the cross correlation between the two. And so what we do is we just introduce a free parameter that just is the ratio between the lensing and clustering amplitudes, which we call x. And so you can also think of this as a ratio between the galaxy bias inferred from the two types of experiment. But it's broadly lensing divided by clustering. And then we say if x lens is equal to 1, that demonstrates internal consistency and means that our analysis, our two data vectors can predict our third, and any deviations from 1 mean indications of that one of the amplitudes of one of those signals is unusually high or low. And so we can do this individually for each redshift, each of our lens redshift bins. So the 4 black points here are our fiducial magnitude limited sample analysis and show really great consistency with x lens equals 1. So this means no worries, this is just an internal systematics test that we pass. That's great, we can move on. The interesting thing happens both at high redshift and with our red sample. So our red magic galaxies are shown by the blue points. And you see that overall there is this offset of x lens less than 1, which turns out to be a sort of few sigma significance when you combine all of these bins. And also both of our samples have a low x lens for the very highest lens redshift bins. Apologies if you can hear the sirens, that's nothing to do with me. So what we ultimately find is that the fiducial analysis is fine, so we don't need to worry about the systematic for that, but for the red galaxies, it appears there might be something interesting that we want to understand. Either the clustering signal is too high, the lensing signal is too low, or this is just a statistical fluke. And so over the summer, we've published a number of papers, we've released a number of papers to try and investigate this. So the first thing that we look at, of course, is there a systematic in your clustering signal? And so we test the clustering signal against various foreground systematics maps. Maybe it could be some observing quantity, maybe it could be some astrophysical quantity that correlates with our clustering signal in a way that we don't expect, and we find that there is no known systematic that can explain a deviation of this size. We then consider maybe this could be foreground lens photometric redshifts. Photometric redshifts are notoriously difficult to do. Maybe we've got them biased in some way. But we find when increasing all our photometric redshift uncertainties or introducing new parameters to describe them, we don't find any shifts in cosmology or this X parameter. So it doesn't appear to be a photosy problem. And then finally, we split our data up into various different ways, splitting up small scales and large scales, and all the different redshift bins, and again, finding no real difference in our cosmology or our X-lens influence. So it appears that this is a real effect that currently can't be explained by the methods that lensing and clustering surveys typically use. So what's going on? We have a follow-up analysis in the works that we think demonstrates that the red magic signal at low redshifts appears to have a high clustering systematic that is currently unknown and is currently part of something that DES is working on, but shows that this only affects the very reddest end of our galaxy distribution. So when you select any large quantity of galaxies, this isn't going to appear, but at the very reddest end, when we only select galaxies that sit exactly on the red sequence, some systematics start to appear. And this is something that we're currently working on understanding. It does appear that this high redshift result isn't related to any clustering systematics, though. And this appears to be a genuine lensing is lower than we expect lensing to be for redshifts above around 0.9. This is something that we don't understand, but is cosmologically interesting, I think. So a number of different surveys in different contexts have found lensing signals being lower than predicted, either predicted by clustering, either predicted by the CMB, or whatever it is. Multiple lensing surveys in multiple different contexts have found low lensing signals where we don't expect that. So this could be that there's some lensing systematic we don't understand. It could be there's something more physics related that is interesting, or it's to do with our prediction of what the clustering that we're calibrating on is how we calibrate the lensing signal with the clustering. But either way, it does appear that there are some low lensing signals at high redshift in the DES data that we don't use in the fiducial analysis that is interesting. Is an interesting data point in this broader lensing as low puzzle. And so the most famous result is this lensing as low paper from Alexis Leteau that shows lensing signals generally falling below what you would predict from the clustering in around Boss galaxies. And so we have investigations ongoing to try and understand whether there are connections between these two lensing as low signals and what we can do to try and resolve them.
Jack, can I ask you something? Sorry.
Yeah, absolutely.
So for this X lens that you're plotting, what sort of scales is this measured on, and do you find any scale dependence in this?
Yes, so good question. So the scales that we're measuring on are, I believe, the fiducial analysis with everything above 8 megaparsecs across the board, and so that is above, kind of 10 arc minutes or something in our correlation functions. And all of these measurements are using all scales above that. So this is like averaging out all our scales between like 10 arc minutes and 250 arc minutes, like a few degrees.
And while you're at it, what is exactly that's being ratioed there in X-Lens? What are the actual observables that go into it? And do those depend on cosmology?
Yes, so that's a very good question. So what's happening here is, so this X-Lens is effectively, what we've done is we've effectively added, so this is a 3x2 analysis with your cosmic shear, galaxy-galaxy lensing, and galaxy clustering, all included in your data vector. And then you say, let's introduce X-Lens as just a free parameter that between the amplitudes of the galaxy bias you would infer from galaxy-galaxy lensing and from galaxy clustering. So it's the equivalent of saying, when you're doing a 3x2 analysis, rather than having the same galaxy bias parameter for your inferred from your clustering and your galaxy-galaxy lensing. Let's make them different. It's the ratio between those two. Okay. So it's very similar to, if people are familiar with like stochastic bias and measurements of stochastic bias, this idea that you might infer different galaxy bias from the lensing, but it's way larger than that. So we would expect stochastic bias to be like a few percent. This is like a 20% deviation. So we don't think this is really being explained by anything physical. It appears to be systematic in the data.
In other words, it could absorb a R correlation coefficient in the bias as well.
Exactly. But my understanding is that R correlation coefficient is theoretically unlikely to be this large. And so we have a somewhat, our prior should be shifted towards the explanation for an X lens not equals 1 not being dominated by R.
And so then just to follow up on this more, so then for R, I guess like, I mean, like, so you are shot noise correcting, I guess, the 2-point measurement of the bias, right? And so for your shot noise, like, are you assuming that it's just Poisson?
Yes, so that's a good question. So yeah, the shot noise is all added to the covariance matrix as if it is Poisson, so our first correlation, our first covariance matrix that we produce assumes that the shot noise is Poisson. What we did do is we measured the high L power spectrum of our lens galaxies, and then said any excess at the very highest L that you see, that indicates a kind of super Poissonian shot noise. And then say what happens if you then input that back into your covariance matrix and redo the analysis with that additional observed shot noise, and this effect remains. So we did do some studies to try and understand whether or not that was non-Poissonian shot noise. It appeared, at least by adding that to the covariance matrix, it didn't explain it.
Okay, great. And then for my previous question, so do you see any evidence for scale dependence in this?
Yes, good question. So that is the result shown in these figures here. So this is the measurement of just S8 from small scales and large scales. Apologies, I don't recall what scale we split on. But you do at least see that the S8 constraint is pretty much the same from both of them, which is probably indicating that X doesn't improve. There is a bit of a small shift in omega matter that could be interesting, but I think this is generally indicating that it's not broadly explained by, or at least the low redshift X lens stuff isn't broadly explained by something with scale dependent. The high redshift stuff, maybe that's something we need to look into.
But this plot is not showing your X lens, is it? I mean, like this is showing your cosmological parameters.
Yes, sorry. So we never actually explicitly ran that for X lens, but the idea is, let's see if I can go back to here. Yeah. So what we have demonstrated is that if you allow X lens to vary, this 2x2 cosmology effectively, well, I mean, it's perfectly degenerate, but the idea is the reason why S8 is so low is because of this X, that there is this degeneracy within the 3x2 analysis. And so if you were to fix X lens entirely on a global level, you would expect S8 to go up.
I see.
And so that was our thinking here by saying if you measure S8, it doesn't go up when you split large and small scales, so we don't think it's a scale dependent thing.
Okay, great. Thank you.
Okay, excellent. Yes, so this is a puzzle that we have a couple of follow-up papers to try and analyze this that are still in the works, but I think this is an interesting area that we need to think about for LSST and for future galaxy-galaxy lensing analyses, because it appears to be a puzzle that is yet to be used.
I mean, I guess the comment is the lensing is low is only low if you believe that the Planck S8 is right? So for many of these measurements, there's a degeneracy between the cosmological parameters. This is somewhat separate from the this X lens issue.
Yeah. Yes. Absolutely. That's definitely true. And I'm here also including like the kids low sigma rate, and claiming that this is a lensing is low issue because the lensing overall, that means your cosmic shear is low. But of course, that is entirely degenerate with sigma 8. I think the difference.
Is it fair to say if you ignore this X lens issue and you wanted S8 of 0.76 with an omega matter around 0.3, would that be consistent with all your DES measurements?
I think the problem is that we're moving in the wrong direction. I think I would have to think about this a little bit more. I think in order for this to be a sigma 8 issue, or a lensing is the correct sigma 8 value, I think we want our X lens to go up. Which is
ignore X lens for a second, right?
Yeah.
If you just look at the data, at face value, is that consistent with all your measurements?
Yeah. So we've said that our best way to put this. Yeah. So our lensing results are consistent with Planck, but also consistent with the lower sigma rate from kids, and that's the same result whether you include the stuff about X lens or not.
But it's true. You also include the red magic, right? The one
yes.
on the next page or a few pages down.
Yeah. So the same thing happens with red magic, but I don't. I think the important thing to state is that we don't think that this low galaxy clustering tangential shear combination. It seems unlikely to, at least to me, that this is finding the true S8 value, and that the cosmic shear is wrong, or the cosmic shear is biased high by a few sigma for some reason. It's possible.
There's a sweet spot in there where almost everything is within 2 sigma, right?
True, absolutely. Yeah. I think that's definitely true. And there is a point in this parameter space here where you could say, it's not far from this point here, right? So that it is possible that we all keep improving our error bars, and we all just focus in on this area that, by our misfortune, is a couple of sigma away from Planck, but that's fine. Right. I think that's a possibility, yeah. Okay, great. I don't have a huge amount of time left, so I'm going to quickly go over. I wanted to do a what's next. So this was we have a year 3 extensions project coming out, which is going to look at more models. So this is looking at what are probably upper limits on modified gravity or other dark energy models when you use the DES Planck combination or DES with other external data sets. There's also a couple of follow-up analyses that I mentioned looking at the red sequence selection that indicate that the red sequence selection is where this systematic is coming from, and that it's not it's less likely to be a real cosmological issue. And then going forward over the next couple of years, we're expecting the full year 6 analysis. So this is deeper imaging, which can get us denser lensing catalogs, so our higher signal to noise overall, and higher redshift lenses, which mean that we can more accurately probe this X lens issue and see whether or not there is a lensing is low, maybe it's some systematic. We'll all try and understand what's going on there. And in order to do this, we have to understand these high redshift lens systematics and understand the blending of our objects, which is why this is going to be a really nice analysis as a test bed for LSST, because it's dealing with exactly the kind of problems that the LSST is going to have to deal with. I'm going to very quickly, over the last 5 minutes or so, talk about baryon acoustic oscillations. Apologies on my time management. The idea is that our clustering signal, not only can we use this as a sort of tool to calibrate galaxy bias and get sigma 8 measurements, but we can also use it as a distance probe itself from the DES data. So the idea here is the early universe predicts a particular scale that we expect to find matter on galaxy distribution to be preferentially find pairs of galaxies that are preferentially separated by a particular distance, which from the early universe physics and the CMB you can predict to be around 100 megaparsecs. And so the signal here is the galaxy clustering signal, so the pair counts of galaxies separated by distance with a non-BAO template removed, and we're trying to measure this bump. If you measure this bump as a function of redshift, that effectively acts as a standard ruler that you can use to directly probe the expansion of the late-time universe. And so we can do this with dark energy survey data itself. So this is purely photometric BAO analysis. So unlike most BAO, which is spectroscopic, we are just using the imaging data. So we have a really nice tangential to the line of sight BAO measurement, but basically absolutely nothing in the redshift direction. So we can do kind of half of what BOSS or eBOSS do on the BAO side. And so we use this with a slightly different selection of red galaxies. It's slightly simpler to the 3x2, and it doesn't appear to have the same systematic issues as our red magic galaxies, which was nice to find, and generally at higher redshifts. So we're looking at redshifts between sort of 0.6 and 1.1 rather than the kind of 0.2, 0.3 kind of redshifts that we used for the lensing analysis. All the same systematic procedures. Analysis was performed blind with mock catalogs, which was a lot of where my work went into. The how to test the analysis was robust before we unblind and ruin it for ourselves. So these are our measurements. You can see we do this analysis in both real space and Fourier space. So we're looking at pair counts separated by angle and a power spectrum, all with the non-BAO signal subtracted. And you can see that in any individual tomographic lens bin, each redshift slices, the signal is pretty weak. But when you add all these together, consider the covariance between the real and Fourier space analyses, what you end up with actually quite a nice BAO distance measurement at a redshift of around 0.8. So each of these tomographic bins, in at least the 4 highest tomographic bins, gives us a BAO measurement itself. So this is, as a function of redshift, the angular diameter distance divided by the sound horizon, which is the observable that tangential BAO is most sensitive to. And you can say from the Planck, from Planck within the lambda-CDM model, we can predict what we expect this to be, and so we're divided by the Planck prediction. So any deviations from 1 indicate tension from the expected expansion history. And you can see that broadly the tomographic bins are consistent with each other, although slightly lower in the high redshift bin, but not statistically significant. And then when we compare this, and we can combine all these, especially averaging them all out at an effective redshift of around 0.8, we get a 2.7% measurement of the angular diameter distance at a redshift where that's actually quite interesting. So we're really quite competitive with BOSS, eBOSS constraints on the diameter distance. Although of course BOSS and eBOSS are spectroscopic samples, so they've also got the direction that we have zero information for. But it does mean that we are able to shrink the error bars at this redshift by a noticeable amount. We're a couple of sigma off Planck lambda-CDM, but given the number of times this BAO signal has been measured, I don't think we find that to be particularly compelling evidence for deviations from lambda-CDM. Given that BAO has been measured a number of times, we probably expect a couple of 2 sigmas to be turning up at this stage. So we think this is pretty consistent with what's come before. Of course, with DESI, that's going to blow this all out of the water. So this is a now somewhat outdated DESI forecast of what you expect the same measurement, just utilizing the fact that you've got more than over 10,000 square degrees of imaging data to go into DESI. You're going to measure this down to less than 1%, which is very exciting and is going to supersede anything we do with DES. But until this is full DESI, so this is years in advance, and so we're hitting this time window where the DES results are cosmologically interesting for at least a few years.
Jack, can I ask something? So the y-axis here is so this DM I thought was some sort of combination of the transverse angular diameter distance and the longitudinal distance. But I thought you were saying that with DES you have essentially no sensitivity, to the line of sight direction.
Yeah. So yeah.
So your measurement, I guess, just is DA. Is that right?
Yeah, exactly. So this is a particular choice that we made, I think, just to compare to BOSS and eBOSS to make that comparison easier. It's not necessarily the thing that we're most sensitive to, but it's the thing that is typically shown from a perspective.
Oh,
And
no.
so all of our information on that parameter is coming from tangential to the line of sight, and we're effectively just averaging over redshift bins.
Yeah, so okay, like I guess I'm just trying to understand like why you have any sensitivity at all. So so you're measuring DA, but you're smearing out over some redshift bin, right? And your redshift bin is what, like 10% or so in width, is that right?
Yeah, they're all about 0.1. Yeah, they're all about a width of about 0.1.
At a redshift of like 1 or so, it's showing here.
Yeah.
Right. So okay. So you're smearing out over some line of sight distance of like several hundred megaparsecs, right? So doesn't that then smear out like the angular location of the BAO peak?
Well, so we're measuring an average of the BAO peak measured across that smeared out range, right? So the redshift distribution goes into our modeling. So we're effectively saying between a redshift of, so say for example for this bin, between a redshift of 0.7 and 0.8, there is some smearing of the BAO position, and so in our fitting code, we have basically averaged over that redshift distribution and said, does our BAO result, does the peak that we observe fit the data that you would expect? So
but you're smearing out over like hundreds of megaparsecs, aren't you? And then if like the entire feature is like 10 megaparsecs in width, at a distance of 100 megaparsecs, lag, I would just think that smearing out by hundreds of megaparsecs would just like kill the sensitivity entirely, but you're saying that it doesn't, huh?
Well, so that's certainly not. I mean, you can see that individually, that the size of the signal that you would expect to find when you average out over that redshift bin is effectively this line here. So it's so it may be difficult to tell on these plots, but it's basically imagine a flat line running through all of these. And that's the no BAO signal. And then with the BAO, we're expecting this very small dip. So individually, none of these bins are high enough signal to noise that you can measure them for exactly this reason, because of the smearing out. But when we add enough data, and you just say, have a single alpha parameter that varies all of these, the positions of the peaks in all of these bins, you end up with a signal that falls out.
Okay, thank you.
It's harder to intuitively, visually see the peak when you're doing this tomographically, but it's there when you add up all the bins.
Okay, thank you.
Great. Okay, and then I guess the final thing that I will say is that we can add that BAO information plus information from the DES supernova survey that I was unfortunately didn't have time to tell you about, to the 3x2 cosmology results, and you can see what that adds. So mostly what this is doing is it's constraining some of the parameters that are very poorly constrained in the standard 3x2 point analysis. So one criticism you might have of a 3x2 cosmology analysis is that there is a very mild dependence on, say, for example, H0, and we have to pick a wide prior range for H0 in our inference that is much larger than any of the observations, and there will be some dependence of our final results on the size of that prior, which is generally undesirable. But when you add the BAO information, that gives you at least enough information on H0 that you no longer require that informative prior. It doesn't change any of our final conclusions. We're still consistent with Planck, still all the same X-lens results, but it at least relaxes our any concerns one might have about the prior dominance of 3x2. And we also get improvements on the parameter strengths by around sort of 20%, which is not insignificant. Okay, so in conclusion, I think the DES results have more than double the signal to noise of what came before it. So in terms of statistical power, this is, I think, a really exciting data set and something that we can learn a lot about cosmology from. There's a lot of ongoing work that is needed. So this higher signal to noise has really exposed, I think, a number of interesting things about lensing surveys that we need to understand over the next couple of years. So we all have lots of work to do, which is fun. And I believe we have the higher signal to noise BAO measurement from photometric data only, so something that uses no spec Z. I believe that's the case. If anyone believes that's wrong, letters to my address. I'd be interested to know if I've been lying to people, but I believe that that's the case. And we have, in total, a kind of a consistency with the CNB and quite a nice dark energy equation of state constraint, some pretty tight limits now. So LAMB-CDM is survived our year 3 analysis, at least from a structure formation perspective, but I think there's some interesting results to come. And I'll leave you there.
Thanks, Jack. Questions? I'm not going to ask questions myself. I know too much. Mike.
Oh, I think you're muted.
I am muted. If you go right back to the beginning where you had the for the, I think, the magnitude limited sample, you show the contours for the galaxy-galaxy lensing and for the cosmic shear. I think it's that one. Yeah, that's right. And you said, yeah, so that's good. I think when you show this, like, if you take away the gray, as you said when you introduced this, if you just did it by eye overlap, you know, you'd get a different thing. And you said, well, there's maybe something else in higher dimensional space that's pulling it away from there. So the question is, what is that thing?
Yes, it's a very good question. It is something that we spent a little bit of time trying to understand. The first thinking was, is this like a degeneracy with galaxy bias? Or if that's if there's an individual parameter of galaxy bias or some particular systematic parameter that is pulling you away, we would want to know that, because it would mean our priors on that systematic are informative, and that actually is an interesting thing. What we ended up finding is that there is no, at least within the way that we've input those parameters, there is no individual parameter that appeared to so neatly be degenerate with one but not the other, that helped us to pinpoint why that shift was occurring.
Okay.
You can do a like PCA analysis kind of thing and then identify what it is from that. I think that is possible. I don't think anyone's done it yet.
Interesting.
So we are attributing this to, it's a 30-dimensional parameter space. There are parts of that where our priors are deliberately informative because they're, say, you have a systematic parameter that we've constrained on external data, and then you put a tight Gaussian prior around it. So we have this kind of prior-dominated multi-dimensional space. These kinds of shifts do occur when parameter degeneracies.
Yeah, it would just be nice to know what it was, but I guess you're saying it's some complicated combination of.
Exactly. I agree. It would be nice to know. I'd like to do that exercise. I don't think we can't say, but we at least know that it is not a simple answer of it is galaxy bias, it is photos, something like that. It doesn't immediately fall out of any of the contour plots.
Okay.
Other questions? James?
Yeah, thanks. That was a great summary. I'm still trying to understand the X factor. So I guess one of the complications with the X factor is that these biases are both things that are put into the modeling. So you could imagine other things going wrong with the modeling that then produce that outcome. So I wonder if you have a sense of what this corresponds to physically. I mean, does this mean there is more or less mass around these objects, given a spatial clustering scale? Like what's the physical thing that corresponds to X being low?
Yeah, so I guess it depends on whether or not you think it's low because of the lensing or clustering, right? So I think if you were to modify just the mass around, or the mass of the halos in which your lenses sit, I would expect both observables to change the same way, or at least in a way that is consistent within our model. And so it kind of I think you could interpret it as the lensing sees lower mass halos than the clustering does, but that's not sort of a physical explanation for that. It's not a self-consistent physical explanation.
I mean, is it? I wonder, can you think of it in terms of a scale dependence that the clustering is in effect, probing something about the standard sort of model of structure formation on some larger scale, and the lensing's on a smaller scale. Like one of them's a 4 megaparsec scale, and one of them's a 400 kiloparsec scale, or something like that.
Certainly, the two probes will be affected by different physical scales. So you could separate it in that way. I think that the scales are very mixed, though, because we have quite a wide range of actual physical scale, or of sort of angular scales that we're measuring for both observables, and that corresponds to a very wide range in physical scales at the same time. So I think you would want to come up with a neater way to separate physical scales in that combination, other than something like X-lens, which is pretty crude.
Right. I mean, I guess another question is there a way of breaking the spatial clustering bit into one halo and two halo pieces and getting constraints from them separately? Does that make any sense? Because it'd be interesting then to see, okay, does the one halo piece contrast with the lensing, et cetera. I mean, maybe it's the same with the lensing. Maybe the lensing's also, you want to split it into those two pieces.
I think in our case, we're cutting out everything below some. We have quite a strict scale cut, so we're only really sensitive to this linear galaxy bias regime.
Okay.
You said 8 megaparsecs or something, right? So
yes.
a lower limit.
Oh, you're cutting out. Okay, I missed that. You're cutting out everything below that scale. Okay.
And so so the idea is this is just a total amplitude of your very large scale measurements for both.
Right.
There is still quite a range within that, but yeah.
8 is still, quasi-linear, so it's not pure linear theory, right?
Sure, yeah, and we do have to model the nonlinear contribution to the mass spectrum in influence. Although the impact is relatively small, I believe.
Okay, thanks.
Okay. Any other questions? No, in that case, let's thank Jack again. Very interesting seminar.
Excellent. Thanks very much.
You actually clap there.